So now I want to talk about top-heavy rational functions, and this is when you have a higher power in the numerator. When we do this, most of what we do is going to be the same, except we won't have a horizontal asymptote. Instead, we have what's called an oblique asymptote, or sometimes called a slant asymptote. So you'll see on this first example here, we don't have the function, but you can see that there's a vertical asymptote here, and then this right here is a slant asymptote. And notice it's all about the end behavior. What happens when x gets really large? What happens when x gets really small? Then in the second one, you see the two vertical asymptotes. They don't have the slant asymptote drawn in, but it would come right here. All right, so you see how that works. And then on this last one, it's not a line. The oblique asymptote is actually a parabola. And this is going to happen when the numerator's power is 2 higher than the denominator's power. So like if you had an x cubed in the numerator and an x in the denominator, then you're going to end up with an oblique asymptote that looks like a parabola. To find the oblique asymptote, we're going to be using synthetic division. It won't go evenly into it. It doesn't matter. We're going to ignore the remainder. So on this first one, the first thing, notice it's top heavy. And all these that we do are going to be top heavy, but you can kind of see what I mean by that. X squared in the numerator, x in the denominator. So start by factoring like we did before. So we're going to have x minus 3 and x plus 2. And in the denominator, we just have the x minus 1. So we can see nothing cancels. So the domain, just like before, we're going to say x not equal to 1. Since nothing cancels, I have a vertical asymptote at 1. Now the oblique asymptote. So you're going to do synthetic division. So we're going to put a 1 out front and a 1, -1, -6. And we don't really care. I mean, you don't even have to go on, but we don't really care about this part. About the remainder, we only care about this. So since this was x squared, this is x, so we have 1x plus 0, or just y equals x. So we have a slope of 1, 0 is the y-intercept, so it's going to pass through 0, 0. Just going to do this so I draw it correctly. And here is my oblique asymptote, or slant asymptote. Then to do the zeros, we just do exactly what we've done before, set the numerator equal to 0. So I get x equals 3 or -2. And I'm going to plot my zeros. And then I'm ready for my interval work. So remember, it's the vertical asymptotes and the zeros. So same as before, -2, 1, and 3. So if I test values, let's find the y-intercept. If you plug in 0 for x, you're going to get -6 over -1, so we get +6. I'm going to plot that point and mark this as positive right here. So if I plug in something smaller than -2, like a -3, I'm going to have a negative times a negative, so it's positive in the top, negative in the bottom, so it's negative. Plug in a 2, you have a negative times a positive, so it's negative in the top, positive in the bottom. And something like a 4, it's positive in the top, positive in the bottom. And then we're ready to draw our graph. So to the left of -2, it's negative. And then it changes to positive. So it's going to have to look something like this, using your asymptotes to guide you, using your x and y intercepts. So we get something like that. Then from 1 to 3, it's negative, and after 3, it's positive. So it's going to go something like this. Okay. And then don't forget, you can always check your graph on your graphing calculator. You can see that I graphed that function. And you can kind of make sure, it won't show you all the asymptotes, but it shows you that shape of the graph. All right, let's try this next one. Again, top heavy, and notice it's just 1 degree higher in the numerator. So I'm going to start by factoring. So y equals x times the quantity x plus 3, and we just have an x plus 2 in the denominator. So my domain, x not equal to -2, Nothing cancels, so we get x equals -2 as a vertical asymptote. Oblique asymptote, we're going to do synthetic division. So I have 1x squared, 3x, and then my constant is 0, and it really wouldn't matter because we don't care about a remainder. So we end up with, cross that out, 1, this is 1x plus 1, so we get y equals x plus 1. So I'm going to draw that. So my y-intercept is 1, and I have a slope of 1, so I can go up 1, over 1, or down 1 to the left 1, and then draw that in. 0, set the numerator equal to 0. We get x equals 0 and -3. And use these for my interval work. So we have -3, -2, and 0. 0 is actually our y-intercept as well. So I'm going to plot that point, and I'm going to plot the -3. Okay, so that's all we know so far. Let's look at our signs on our sign chart. So if I plug in a -4, it's going to be a negative times a negative, so it's positive in the numerator, negative in the denominator, so it's negative. If I plug in, say, a -2.5, it's going to be a negative times a positive, so it's negative in the numerator, and negative in the denominator, so it's positive. Here, if I plug in, say, a -1, I've got a negative times a positive, so it's negative in the numerator, positive in the denominator. And plug in something bigger than 0, like a 1, everything is positive. So we have this. So it needs to be negative to the left of -3 and then change to positive. So hopefully you see it's going to do something like this. And then negative between -2 and 0, and then it changes to positive. So it's doing something like this. So then if we graph this, this is what we get. Now you might notice that maybe all my corners are not as sharp as this one, but it's still, you can kind of see that it's a good sketch of our graph. Okay, then going on. Notice what's going to happen on this one. Look, it's top heavy, but take a look at the powers. This is 2 higher. This means that our oblique asymptote is going to be a parabola. So there is nothing to factor. My domain is x not equal to 1. And my vertical asymptote is x equals 1. So I'll plot that. My oblique asymptote. So I'm still doing synthetic division. I'm going to do the 1 out front. And we have 1x cubed, 0x squared, 0x, and 0 for our constant. So bring the first number down, we multiply, we add, we multiply, we add, we multiply, we add, but we don't care about that. So if this was x cubed, then my answer is x squared. So x squared plus x plus 1. That's my oblique asymptote, and I have to draw it. So I have to sketch that. So think about what we need to know. We need to know the vertex. So to find the vertex, we're going to take the opposite of b over 2a, so we get -1/2. Then we're going to plug in that -1/2 to find the y value. Okay, so I did it, I paused it and did it on my calculator, and I get 3/4. So that's my vertex. Whoops. So -1/2, 3/4, and I'm going to kind of plot where that goes. Now what am I going to do from there? I know it opens up, and I know that it doesn't have a stretch. So from my vertex, I can go over 1, up 1, over 2, up 4. So I'm going to go over 1, up 1, both directions, and over 2, being careful here. 1, 2, 3, 4. Okay, so it's not that bad if you find the vertex and then use whether or not it's stretched, and then I'm going to draw this in. All right, so that's my oblique asymptote. Next, I find the zeros, set the numerator equal to 0. We get x equals 0, so I'm going to plot that point. And my interval work, I'm using my vertical asymptote and my 0. And let's check out the y-intercept. Well, we see that's 0. So if I let x equal, say, a -1, I'm going to have a negative on the top and a negative on the bottom, so it is positive. If I let x be a half, I'm going to have a positive on the top, negative on the bottom, so it's negative. And something larger than 1, like a 2, it's going to be positive in both. So this is what we've got. So to the left of 0, it's positive. And then from 0 to 1, it's negative. Remember, we have a vertical asymptote. So from 0 to 1, it's negative, which means it has to be down here. And it has to kind of hug. So it's going to have to go like this as it kind of moves down closer and as it gets closer to 1. But then what's going to happen over here is, remember, this is about the end behavior. Sometimes it comes on the inside, sometimes it goes on the outside. I'm not really sure what this one's going to do, so we're just going to kind of sketch it in. But it gets closer to that shape. So the smaller that x gets, the closer it gets. I think this one might come on the outside and then get closer, but we'll see. And we really just have to have kind of a sketch. So we use the asymptote, the oblique asymptote, to guide us. And then from 0 to 1, I already did that. From 1 on, it's positive. So this is kind of unique because it can't be on this side because it can't be negative. So it can't be over here because if it was over here, then somewhere it has to go negative. So you see this little region in here? If it's always positive to the right of 1, then it's going to have to stay somewhere in here. And it actually does something like this, which is a little strange, but that's what it looks like. And we can check it out on our graphing calculator. So here it is. So you can kind of see how that does match what I drew. It's great to have the graphing calculator. I do want you to show all this, you're analyzing this graph, you're analyzing the rational function, and using all this information, and then using the graphing calculator definitely to check your answer. We want to make sure you do that. All right, let's try this next one. So we're going to do, start with our, I'm going to factor this. Okay, and here we go again. Here's another issue. When we factor this, we have to factor this polynomial. It's an x cubed. So you have to think back to what we just did. We just completed a unit on factoring polynomials. So we have to think about the p's and q's. Remember that? So we're going to start by doing synthetic division so we can find out how to factor this. So our possible rational roots are plus or minus 1 and plus or minus 2. So you're going to use your graphing calculator. You're going to type in the numerator. We're just trying to factor the numerator like what we did in the last unit. So once you do that, if you go to your table and type in the 1, -1, because plus or minus 1, plus or minus 2, you'll see that 1 is a root. So we're going to do synthetic division with a 1. Now notice I'm only using, I'm just working on my numerator right now. So we have 1x cubed, 1x squared, 0x, and a -2. And this time we do care about the remainder. We want it to be 0. I mean, we know it's going to be. Okay, so good thing we got that. So that means so far I know that it's going to be x. If 1 is a root, then x minus 1 is a factor. And this is going to be x squared plus 2x plus 2. And that is not factorable. X squared plus 2x plus 2, oh, yeah, not factorable. So we're going to have to work with that on the zeros because in just a minute. So right now it factors to x minus 1, x squared plus 2x plus 2 over x plus 1. Okay, so that's how it factors. So to find our domain, we're going to look at the denominator. So x not equal to negative 1. We are going to have a vertical asymptote at negative 1. Then to get our oblique asymptote, remember what we do next. We're going to do synthetic division with a negative 1 because we're just working with this now. We're putting this off to the side. That's going to come in handy for our zeros. So we're going to have a negative 1. And we had 1x cubed, 1x squared, 0x, and a negative 2. This is the time we don't care about our remainder. 0, 0. Oh, this is going to at least be nice. Did I do that right? Multiply, add, multiply, add. So we get, this is x squared, and this is a remainder we don't care about. So we get y equals x squared, parent graph. So that's not bad. So over 1, up 1, over 2, up 4. And dash that in. Okay, now we got to do zeros. Well, we already know one of them, x equals 1. What we have to find out is, are there any zeros from this? It's not factorable, which means we need another method. So let's do the quadratic formula. So x equals the opposite of b plus or minus square root b squared, which is 4, minus 4ac all over 2a. So right away I can see this is going to be 4 minus 8, which means it's going to be imaginary. So it's non-real, and we're only dealing with real. So we don't need this. We don't have to worry about that. The only zero we have is at 1. But we had to check that, because it's possible we could have had some irrational roots that would still fall on here. So now we're going to use our vertical asymptote and our zeros. Y-intercept, if you plug a 0 in, you get negative 2 over 1. So 0, negative 2 is our y-intercept. So I'm going to plot that. And so that means this is a negative. Something smaller than negative 1. So if I, oh, this is going to be a little harder to do. If I plug in a, say, negative 2, it's going to be negative here, positive here. So it's negative on the top and negative on the bottom. I'm going to stop and check this. Okay, so it's negative on the top, negative on the bottom, so it is positive. If we take something like a 2 and plug it in, it's going to be positive. This is going to be positive. This is going to be positive. So we have a positive. So now, to the left of negative 1, it has to always be positive, which remember, that means it can't, because it can't come down here, and so it can't be on the outside. So this is one of those ones, let me change colors, that's going to be like this. Okay? Then between negative 1 and 1, it's negative. Okay, and it passes through my y-intercept, and then it switches to positive. So it's going to do something like this. And then it's going to start to hug this parabola. The larger x gets, the closer it will start to follow into that pattern. So we get something like this. Okay, so when you graph that, you do end up getting this. Okay. And the next one, we are not going to do. You'll notice that it's a little messier because it's an x squared here and not just an x. So we're actually going to skip this one. I might come back and do this one later, but not right now.